Record. Sorry about that. So we're in review for people who are just jumping onto the recording. We're just in review, turn the recording on about 4 or 5 slides in, and we're going over the stuff from the last lecture. Okay, so that was kind of the big point of that one. And then we talked a little bit about different ways to protect a base class so that it cannot be instanced. And we said that there's really no keywords like abstract when you talk about abstract classes. In C++ anyway, it really just derives from the fact that you have at least one pure virtual function. So on the previous slide, we were talking about virtual functions, which is what we need to allow that collection of pointers to creature to work properly. But if we set a virtual function equal to 0, that means we've removed its implementation, and that will prevent this class from being instanced, although it can be combined with an instance of a descendant class, but you can't actually instance it by itself. That's what it means to have an abstract class. And we tend to do that kind of thing when we just want to set some basic parameters and be assured that the base class will never actually be instanced. So that's called pure virtual, right? For that particular method, which causes the whole class to become an abstract class. It's not easy to discern that if you dig through the literature. So if you can remember that relationship, it'll save you some trouble when you come around to it next time, okay? And then the other thing we talked about was an interface class. An interface class is kind of like an abstract class. It just doesn't have any data members, right? We have at least one pure virtual method. And then in our interface class on the right side, it's just, there's no constructor, there's no data members. This certainly can't be instanced. And it really is just there to specify the function signature, if you will, that all deriving classes need to follow. And that's a very, very useful thing for third-party development software. I was looking at Unreal Engine for last night just to kind of crawl through some of their classes, and it's fascinating but a little bit heavy reading. But they have hundreds of classes that, and I think they derive about 3 or 4 levels deep, but it broadens out very quickly, and you get tons and tons of different classes. It's really quite instructional if anybody is interested and wants to look at what it's like to walk through classes for a very reputable, large, software development project. That's a great one to start with. It's called Unreal Engine 4. So that's our abstract versus interface. We also did a little bit of quick introduction to this idea of reclassifying whether a particular member or method is public or protected or private. And we said we do that with the using method or the using keyword. All we have to do is invoke almost like a prototype, right? We say the name of the member or the method with the word using in front of it, and it pulls it into the public or private area of this descendant class. So that's how we actually either hide or expose something. And we looked at both of those examples in the last exercise or the last class. So we've requalified foo-x, which was protected here, to be public down here in the Foo Junior class. Okay, just check and make sure I got everybody with me. Yep. Okay. Okay. So we could do something like the first line here is okay. FooJunior.x is great, but if we use that scope to try to access the base class, we get the error because, of course, it is protected in the base class. Okay. And then we looked at 2 things relating to multiple inheritance. We, of course, saw inheritance, but this is sort of the typical parent-descendant kind of idea. You have 2 parents, and you're aggregating the features of both of those base classes into a child. Here we call Fugu. And the key syntax to remember here, and it's easy to get confused. Remember, there are two ways we use public. The green public there is kind of indicating the status of our members, but this public up here in blue indicates how we're going to pass on the traits that we inherit from foo or from goo. And that public foo, comma, public goo should not be confused with our constructor initializer list down here, right? So here we're calling the constructors, we're saying how they're going to get called, but this order has nothing to do with the order in which they get called. They'll actually get called in this order, foo and then goo, by virtue of how you've actually done this descendant or this inheritance syntax up here. Okay. So that's how we do the multiple inheritance piece. And then we introduced just one small problem that can happen when you're getting really intensely into some large chain hierarchies. We said this is called the diamond problem, and the way you get around it is by introducing this special keyword called virtual. When we derive publicly, we tuck that word virtual you see there in and to the class that sits right below the potential conflict. And at runtime, things will get sorted out for you. So you really only end up with one copy of person in this packet of instances for the grad instance of the class, the descendant class. Okay, so that was the diamond problem, and the virtual keyword there, used differently than we saw it with the method in the class, but it lets us avoid this particular problem. Okay, so there it is. Okay, any questions on that before we move on? That's just a quick look back at what we talked about on Tuesday. You'll see that definitely on the next quiz when it comes up. So worth making sure you understand it. Okay, cool. All right, then let's kind of move on into new territory here. And this first one, you have to take a little bit on faith. We're not going to dig deep into the chrono library, but it's the cool and modern way to measure time. There are a lot of less qualified attempts to use things that do exist, like sleep. The keyword sleep, people tend to try to use this in some of their code to put their application to sleep. Not the right way to really do it, not the modern way to do it. And so Chrono is how we'll do that. So Chrono is a really comprehensive library. It goes way beyond anything we would do in this class. But it provides a system clock, so you can deal with dates, real world dates, which is one thing. But also there are two timers that you can use. And they're both very good. You can use them for evaluating elapsed time or intervals of time, often used to measure performance inside of a program. So one of the good questions we had Tuesday about what is the cost of virtual binding versus fixed binding, right? If you don't use the virtual method, right? So how much does that add? So one way we could do that is with these clocks. We can set some tag points before and after and do some quick measurement. But the one that we're going to work with is the steady clock. And if you're interested on the side in a fantastic video that just goes through all this, this link that I've given you here is actually one of the original developers, I think, of this the clock and the spec for this Chrono library. So it's he's quite passionate about it. It goes pretty deep, probably more than you want to know. But so the key thing about Chrono is namespace. So this is kind of the first time we're concatenating multiple namespaces, right? So in order for us to pull something out of the Chrono library, we have to use the std namespace followed by the Chrono namespace, and then the function from the Chrono library that we want to use. So for example, we might say std chrono steady clock time point t1. That creates a variable which is called a time point. And that's a very long way of actually expressing the namespace that we need to get to. So we'll stick with our using std up top in some of our exercises just to minimize the syntax, but we'll still have to express chrono as the prefix before we invoke those functions. And I think that's probably the most confusing thing about this, because it just looks like a lot of syntax. So we'll see stuff more like that, but it's still a little bit annoying to have to go through it. And we could have said using namespace std chrono to either inside of some local scope or at the file scope to set that usage at the high level. But I just left it to help us all remember that these are coming out of the Chrono library. We're going to just keep that chrono like that. Okay. Okay, so let's look at a couple examples. So we would, of course, have to include the Chrono library. We'll set our std namespace, and hold on, let me clear my screen so I can see what's going on. Okay, so this is sort of a conceptual idea of system time. I think you guys get this, and I think we did this earlier in the semester, but the idea is that we create this T1 variable, right? It's just a variable at this point. It's a special variable of type steady clock, right? And so once we get the T1 variable there, then we're going to set it equal to now, right? So steady clock now is whatever real world time it is now, right? And then we'll do some execution, and then we'll create another T2, which we could have done above, because we could declare the variable above and then initialize it to now again at a later time. And then because these are very special and kind of heavily loaded T1, T2 are very complicated instances of a class, we have to have another special item here called time span that allows us to subtract these two. So all of this syntax I don't expect you to memorize, but conceptually, hopefully you understand the notion that we're just going to subtract this instance of a time point T1 from T2, and that's going to give us our time span. So whenever we're measuring something, that's one way we would do that, and we have to kind of measure the time span in seconds this way. So we'll look at that. We'll play around with that for our first exercise, just to get you a little used to working with that. So please have a look at that. The first link for that is in the file that I posted. So the idea is, and let me know, somebody either privately or publicly if you want, put your hand up if you can't see that file. I'm still not totally clear when you join late if you can see it, or if you join after I post it. So just let me know. And I'll repost it. Okay, let me repost it again. Yeah, looks like I should repost it again. Hold on, no worries. This, and then there. Make sure I don't get the wrong one. 26 links, inheritance links, thread. Okay, there we go. All right. There we go. Okay. All right, so we want to create a time point T1, just like we were talking about, get some input from the user, that's you, create another time point after the input is collected from a cin. So this would be like a collecting a word, so you could do a cin to a string. And then create a chrono duration variable, do the subtraction, and then print out using the count method from that duration, all right? So just try that if you would. The code link that you see there should give you everything you need to kind of look through those to-do items. And so what I might do is roll back a screen so you can kind of see the desired syntax that you need to follow here, which is kind of up here, so in this slide there. So take a minute with that, ask me questions in chat or however if you get stuck. And we'll see how that goes. Now, as you're doing this, just sort of a reach ahead to help you jive with this later. Keep in mind that, as you know, cin kind of pauses execution of your program. We've kind of seen that happen, and if you see the cin on, let's say, line 26, you can assume that while you're typing, execution is paused and waiting for you at line 26. It's not progressing beyond that point. And we'll see shortly that that's an example of a thread being paused. In this case, our program has one thread, which is the main thread that we're executing. But that cin is a place where we've gotten used to seeing stuff pause, and that's happening as a result of the cin waiting for input from you. But we'll actually very soon here actually get to do that, create that kind of control ourselves.
Professor?
Yes.
Why do we use the count method?
Yeah, good question. Yeah, count is, if I recall, this is the one thing about the library I don't quite understand, or maybe just don't like. The count method gives us seconds. It would be nice if time span would just be overloaded so that in the cout, it would actually know how to convert the instance to seconds. But that is, to my recollection, that's the best we get right now. And it is seconds, even though it doesn't say seconds.
Huh.
Yeah.
Is
Um,
it like integer or like more like a double? Can you
I
convert it to a
believe
double easily?
I believe it's an integer. You may be able to convert it to a double. Yeah, it's I'm a little rusty on this part of it. I know that all the rest of the Chrono library has a very comprehensive way of converting between milliseconds, seconds, microseconds, all that stuff via keywords, and it's pretty slick.
Yeah.
Time span, if I remember, was the one that was just a little bit brain dead.
Okay.
Yeah, and I'm pretty sure it's seconds. Yeah. Okay, so let's take a look at that. Oh, it's probably pretty quick for you guys, but maybe just getting yourself used to the syntax there. It's a little bit dense, but there's our time point, of course, and we set it equal to now, and then whatever we do here, typing and inputting, takes by vastly more time than anything else. And then we set our time point to now also. We kind of declare it here, and then we set it equal to the now function here. And calculate the duration, and of course print that out. And there's our seconds. So that kind of thing we'll do whenever we're measuring anything. And then next we're going to look at a way to actually use this Chrono library to put a thread to sleep. And that's the really important part for today's lecture, because it helps us actually debug our threads. It's probably not something you would ever actually do in real life, because unless it's a game, but if you're trying to do something very efficiently, you certainly don't want to be sleeping for no good reason. So we'll use this in a couple different ways, but time points is one of the ways that we may come back to measure some stuff as we go forward. So let's talk about putting a thread to sleep. This is where things start getting a little more fun. So this is our first use of the thread library. We're kind of reaching ahead a little bit to ease the pain on some of our exercises, but the thread library is where everything comes from for us. And this particular syntax is really, really useful for us. We'll use it a lot. So I can say sleep for, so this thread is a special syntax. That scope allows us to invoke the sleep for function. And then we use chrono to allow us to specify very clearly either seconds or milliseconds. So we could say chrono seconds parenthesis 1, or I could say chrono milliseconds parenthesis 6 times 1,000 for 6 seconds, just to show you that this keyword here is actually just one of the many ways we could actually express a duration in time that we actually want to actually sleep. Bear with me one second. I'm going to post the links one more time here. Sorry about that. 6, I should keep it handy. Oops, cursor. Sometimes my cursor disappears. There we go. Okay, just in case anybody needs those threads or those links for today. So, that's what we would do to put a thread to sleep. And you can choose whichever form you want, whatever makes the most sense to you. Usually, working within seconds is sufficient. But it's really nice to have those conversions show up in the code like that. It makes it very readable. So we'll use that to slow down our threads so we can debug them and we can create different scenarios. So let's talk a little bit about threads. What are threads? So you can think of them like separate programs that have a shared memory. But the reality is it's really just your one program, your one entire, if you think of your program, any program that you write is this main program with a bunch of functions that are kind of branches on a tree. The execution path of your program and all of your homework assignments that you've done so far, just has one pointer, if you will, that travels through all your functions and comes back out again. Well, now we're going to have on the same tree, if you will, or the same program, we're going to have multiple of these things executing out of sync, asynchronously, right? Depending on what kind of work you want to do. And it's kind of mind-blowing when you think about it, because it opens up a whole new way about thinking about how you might want to do something. Now, where does this come from, this idea of threads? Well, one way to think about it is, if you've heard of multi-core architectures, multi-core CPUs, or a computer that has multiple CPUs. So typically multi-core is, multiple small CPUs working in tandem with access to common memory. And that's a very, very modern construct. So a quad core machine would have 4 cores, and at a minimum, that means you can have 4 concurrently executing, truly concurrently executing threads going on at the same time. Now, because of operating systems and how fast computers are, operating systems can grant us hundreds of threads at the same time. So even though I only have 4 actual cores and I can only really ever have 4 things executing at the exact same time, operating systems can make it seem like I can have hundreds. And they'll just give access to these threads super fast in a very quick way, so that it seems to us like our threads are all executing simultaneously, and asynchronously, right? So that's really nice. Obviously, if you have a 4-core machine, you create 1,000 threads, you're going to grind your machine into the dust. But we can have as many as we want until the performance of the computer starts to suffer. So the nice thing about it is we can think about these things logically. We can say, okay, I have a task to do, you have a task to do, there's another task someone else has to do. Okay, I'm going to need 8 threads, and I'll resync those threads every so often. So for example, main, I said, has kind of been a thread we've been working with all along. We just didn't really know it. Now we're going to look at a way to spawn an extra thread, and we'll spawn it by calling a function, essentially, and that function will go off and start doing some things, and it could call other functions. This process can go in so many different directions, right? So, but we need to think completely differently about how we want to get some jobs done. So for example, let's say you had 4 tasks that you had to do in your program, and the order didn't matter, right? It's not like you had to read a file and then add some numbers. Let's say you could do them wholly independently of each other. Maybe 4 files needed to be read, and they could all be read at the same time. Well, we could call the same worker function in 4 different threads, and we could be reading 4 files simultaneously. And if they were really big files, and they all finished roughly around the same time, we get our job done faster, right? We're utilizing all of the power of the machine to process these files or do some math, for example. Another example I can tell you, a real one, is, so one of the physics company that I worked at, our software ran on all the consoles, PlayStation and Xbox, and the math for actually doing physics, if you're clever about it, you can decompose into non-dependent threads where you can do, and all this is happening in a 60th of a second, but you can go do a bunch of math on one thread, and then you can do a bunch of math on a separate thread for parallel islands where physics isn't interacting. And then you can have a final thread aggregate that stuff all together when the previous threads are done. So, and you might think it sounds like a small task, but it's a difference between having, a game that actually, you can knock things around and jump around, and something that just is kind of a toy. I guess they're all toys, but pretty impressive difference, really, when you really take advantage of all the power that a multi-core machine has, and all these.
Professor?
Yes, yeah.
Company did you work at?
Havoc.
Dude, you guys did Half-Life too.
Yeah, that was very early. We licensed the library to them. That was a super early version of the library. But basically, anything, I hate to say it this way, but any game that had a dead body falling for about, down upstairs or something and bouncing around for about 7 years, that was us. Before, there were a few other competitors that entered the landscape.
Awesome. Wait,
Yeah.
you took part in the creation of like ragdoll physics?
Yeah, that was what we did. I mean, I wasn't the engineer. I wasn't the lead engineer, but I was the product manager for the company. So I had to go to all the game companies. So,
That's really cool.
Yeah, but quite so many wonderful examples of how people are really using these concepts, and it matters. It matters in microseconds ways, but in aggregate when you do these things, because if you have a thread sitting there idling, so imagine, I mean, I won't belabor this too much, but let's say you're Electronic Arts and you just, committed all of your development cycles to use the latest console game engine or game platform that came out. But you're finding out that one of your threads is sitting idly, like, you're not using one of the 4 cores of that thing, and your game could go that much faster. And it turns out it's Havoc's library that isn't optimized to fully utilize all the threads. Well, you're going to be very unhappy about your investment in Havoc software. So it's really incumbent upon the engineers to maximize the throughput of their software by utilizing these threads to their absolute fullest. And it can make a really, really big difference. It's quite profound. And, and just to take it out of the game context, Autodesk, goes to the same thing. If you're ever contemplating, Maya Max or 3D Studio Max or any kind of film effects rendering, and or your Pixar, for example, and your frames take 5 hours per frame, and you have 100, 500,000 frames per movie, but your extra threads are sitting there idling because you haven't figured out how to render one horizontal scan line on one thread and render the next horizontal scan line on another thread. Well, that's a real waste of time, right? So those things, I can assure you, the Pixar software and the Autodesk rendering software and all the big, film effects class renderers are all very, very well threaded. So this is what's so cool about this thing. It's very relevant in so many ways. And not to just make it entertainment based, but any computationally scientific problems that can be decomposed into separate threads mathematically can be and cleverly aggregated together again at the end, win big time by doing multi-threading. But you have to understand kind of how to decompose your problem into that way. So that's the whole point of this. So that's great. I'm glad you guys kind of recognize that. So and one of the key things we'll see here is that the tricky part is when we access the common data to put our data back or to take some data out, sometimes there's data that all these threads need to be able to check back and forth on. Sometimes we can divide up their workload sufficiently so we don't have to worry that they overwrite each other. But very often there's 1 or 2 or 3 little pieces of data that they have to synchronize. And if you don't do it the right way, it's just like fighting with your brothers and sisters over the last piece of toast or donut or something. It's just not nice. So here, let's get into the code. So what we're going to do, like we saw with many things so far, starting with the shared pointers, is we're going to create an instance of a thread and give it a name, right? So it looks like a variable, but it's actually an instance of a class, of the thread class, right? And that thread instance, as you can imagine, has lots of methods associated with it and private data as well. And what we need to do, though, to kick off the thread is to actually feed it a worker function with some arguments that worker function needs. And that starts the process of this thread. It just goes off, right? It's like, here's your task, go for it, right? So typically we will see a worker function do work. It could be fed to a thread this way, right? So I can create thread, my thread 1, and then pass in the name of the function. We don't invoke the function, right? We don't say do work with parentheses. We just say, hey, here's the function, you call it, right? I'm not going to call it, you call it, because you're the thread manager. But here's the function I need you to call, right? So that's how we pass that in, right? So that kicks off the work for that specific thread. And that's happening from some other thread, right? Like typically main for simple examples. But we could call the same function over and over again on different threads, and that's okay. They're what we would say is reentrant, right? There's nothing, we would write these do work functions so that there's nothing existing here or happening here with variables that in any way could affect another thread's execution of the do work function, right? If it's local variables inside and no static variables inside of the do work function, then these things are completely separate, right? And so even though you look at it and think, well, that's one function, how could both threads be using it at the same time? Well, they have their own copy of the function, right? So we can do that with one function, or we could have lots of functions. It really doesn't matter. It depends on what job we're actually trying to get done. So let's kind of crank up the complexity a little bit, and feel free to stop me here if it just gets a little too deep. I tried to illustrate everything here because these are strange concepts. I'll also point out, I don't know if you can see this kind of sound box up here, or the speaker. So I've recorded hopefully what I'm telling you almost identically on a lot of these slides. You can come back to them, and I would encourage you to do that. Of course, you can watch the video, but if you ever have the PowerPoints and you just want to click on these, you'll get this particular lecture today has a lot of this stuff in it because this is some dense stuff. But so here's what we would do. Imagine our main thread kind of traveling left to right there, and we decide, okay, we got some special work we need to get done in thread number 1 here. So I'm going to spawn a thread just like we just saw on the previous slide there. We'll think of that as our thread number 1. We'll think of the main as thread 0, right? And then we're going to spawn another thread, right? And so that's going to go off and start doing some work, okay? And then just to put all this in context, we're going to have our cin here again. We're going to ask for some input. And as I mentioned just a few minutes ago, the cin is going to pause the main thread. So this is an example of a function that's going to pause the main thread because it needs to, because it needs input from you. Obviously, if it didn't pause, you couldn't possibly type fast enough to fill up the buffers with characters so that you could actually get that information into your program. So it's pausing for you. Once it's done, it's going to continue. And we need, in order to really re-aggregate any feedback or execution kind of closure from our other threads, we have to rejoin those threads, right? We have to express in code, and we'll see that in a minute, that we want our thread 2 back, right? And then again, we have to express that we want our thread 1 back. And the reason we do that is because if thread 2 is not ready to rejoin, main is going to wait here, right? It's kind of like do not pass go until, if you said you want thread 2 back here, we're going to wait. Main is going to wait here because it's off doing, maybe it's doing some very heavy lifting. It's not done yet. We're going to wait, right? And as soon as thread 2 says, hi, I'm back, I'm done, it returns from its function, right? Whenever that may be, then main can continue. And here, then we'll pause again and say, okay, we're going to wait for thread 1 to rejoin here, okay? So it's going to pause again. And thread 1, maybe it was done a while ago, right? Maybe it was already there waiting for us, right? Maybe thread 1 was done before thread 2. And so I have a momentary pause to realize, oh, thread 1's already here. Okay, well, now I'll continue. And then my program can finish. And the key takeaway here is if you do not rejoin your threads, your program will never finish. Main will, you'll potentially either run into a crash or you will just not exit the program. And then of course you can forcefully crash your program, but that's not clean execution of your threads. And if you were doing anything, on a large scale, that would obviously you lose quite a bit of data and something wouldn't go right, right? But that's the structure of how we have to work with threads in C++, okay?
So you could say that when we use a debugger for our console in Visual Studio, we're actually pausing the main thread.
Yeah, absolutely, without question. Yeah. And but debugging multiple threads is a different thing altogether because they're all asynchronous, right? Like you have to sort of imagine that thread 1 might be off doing something and it might take a really long time, and thread 2 might finish in a microsecond, and so they're all at different execution phases. And also, although we don't do it in this lecture, but this thread could spawn another thread, right? So you could have threads spawning threads all over the place, which can get really crazy.
And this is the fundamental reason for performance stuttering, because if a thread isn't back in time, then the entire thing has to hang.
Exactly. And as we'll see, if we don't write the code properly, we get thread lock, which can happen a lot. There are some really tricky situations with thread lock where you're just like, what's going on? Oh, we're locked. And then it's like, okay, which thread is locked? Who locked it? Where's the problem? It can get really tough to debug some of this stuff. So let's look at a couple things here. So here's going to be our worker function, and you have to bear with me. I had to kind of make some of this stuff up. Threads are very tricky, and so I'm trying to keep it simple. But our do worker function, we're just going to it's going to expect one argument. integer, some value that we want to pass in that maybe tells us how long to sleep or how much money to spend or whatever. So we're going to say, we're going to create an instance of a thread, and its constructor wants two things. It wants the name of the function, and then it wants any arguments in order that that function wants. We don't want to call the function here, right? If you say do work parenthesis 10, you're calling the function, and when it returns, the return value gets passed to the thread. But that means that do work would execute in the thread of main. We want do work to execute in this thread. So we're passing in the name and the arguments for do work, and we're letting the thread instance itself initiate the thread and invoke this function with these arguments, okay? So it's really important to separate those two, and I realize it's confusing, and many people will just want to put a parenthesis around that 10. Don't do it, because then you're just executing do work before you call the myThread instance or before you construct it. Does that make sense? Anybody confused about that?
When do you rejoin the thread?
Right. So so that's where we started. We can do multiple threads, and then we name the thread. We invoke it through its instance name, and we just say join, and it pulls it back into the main thread. Okay. So and as we saw on that drawing, we will wait there before we continue. And maybe thread. Actually, sorry, the naming here is wrong. That should say thread 2, and that say thread 1. The colors are swapped. Sorry about that. And the order really doesn't matter, right? It depends on your design, right? If thread 2 has to finish before you can collect the data from thread 1, then the order here should be swapped. But I apologize for the color mismatch here, right? I should have kept the purple and then orange. So that's the analogous to what we saw on that previous slide, right? Okay, and again, we can send in the same function with different arguments for that function. And these two things, assuming there's no static or global variables inside of the do work function, they're not going to collide with each other because they're using the stack, right? Like we know kind of happens with functions. And so, so they have their own local copies of everything that's going on. A lot like recursion, actually, right? When we do recursion, we're putting different copies of the same function on the stack. So you can think of it that way, okay? So those are our do work functions, and that's our finish, right? So so let's look at a way to do a simple do work function, and we'll get into our next exercise here. So we pass in a value here. I think I called it max. And so what we're going to do is we're just going to kind of consider max to be units of work, right? So every loop we're carrying out 1 unit of work. We'll say doing work number such and such. And so we'll count from I equals 0 up to whatever value gets called with do work. And then, and this is just for our debugging, we're going to put this thread to sleep, right, for 1 second so that we can kind of see what's happening, see as it's executing. Okay, so that's that syntax we saw earlier. And then whenever we call this function, it doesn't matter how many threads call this function, they all get their own local version of it. And maybe you vary the max value on every one of them. So some of them will, you know, do 10 units of work, some will do 1 unit of work. It really doesn't matter, but you know, that's just one generic, you know, do work function that we can call. Right? So here's a little look inside of the thread class. So we of course have our constructor. We've already seen kind of how that's going to work. We pass it a worker function and the worker function's arguments. It has, of course, a destructor, which is nice. We've already seen the join. We'll see how we can forcibly detach a thread, which we won't do a lot of work with because it basically just sends a thread off. We can never really get it back again. But we can do some basic things to check and see whether, or to assign, sorry, we can assign instead of constructing it with the worker function, we can assign the worker function after we create the declaration of it. Etc. Or we can also find out if it's joinable, or is it something that can be brought back together, right, with the main. So but that's about it, right? That's the main stuff there. So I can do that. Class name, instance name. We saw this before pretty much. And just a reminder not to use the parentheses there. Okay. And then that number sort of gets fed to the do work function by this thread here. Okay, probably beat you guys over the head with that one enough, but let's try it out. Okay, so what we're gonna do is we're gonna consider that do work function. We're gonna just have you create a thread in main that calls the do work function, and it should print a message to indicate that you are waiting for the work to be done, right? So we're gonna kind of intentionally create this do work function to do a lot of work. So you can print a message in main that says, okay, I'm here waiting for this thing to happen. And then you join back and print out a message for that to kind of to make sure you actually came back again. So give that a try if you would. If anybody doesn't have the links, let me know. Let me just pull my, right, good question. Sorry, I'm just catching up on some questions. How do you deal with functions that don't return void? That's a good one. I think we'll see that on Tuesday. Return values from these functions are a bit strange. And there's a way to do that, but I think we might convert to what are called functors or lambdas, which we'll go over in the lecture or two following this one. So good question, but I'll probably come back to that if that's all right.
For the file that I downloaded, it shows as the practice 2 as the chrono.
Yeah, I'm just gonna have to type it in manually.
Oh, did I bollocks one of the links?
It seems like if you could just put it in the chat, I can copy and paste it.
And it's for the current one for the
Yes.
thread practice. Okay, hold on one second. Oh yeah, I did, didn't I? Okay, hold on. I got you coming right up. Just getting like moving boxes out of the way on my screen. I really do need to get a spare screen. Bear with me one second. So we're on the intro work practice, right? So I'll give you the practice and the solution. Thanks for bringing that up. So there's the practice and there's the solution coming up. There you go. Okay, let me know if that's okay.
Okay, let's see.
I think so. And I'll roll back to that previous syntax just to kind of help everybody out. But let me know if you have any questions on that. But that's how we. I'll do the previous slide because I think that probably has more better stuff on it. That one, yeah. So that's kind of the model we're thinking about there. Okay. All right, so I'm gonna set just a little timer on that and let you guys work on that. These are worth taking the time on. I think they're kind of fun too. It's kind of mind blowing once you see it working, although sometimes it does things you're like, what's going on? Okay, maybe another minute or so. I'm gonna go a little bit longer just in case. So one thing that you may notice, and it's it's an understandable question. You might wonder, where should I put that message waiting for work to be done? You know, should I print it right before the thread is forked, or should I put it after? It kind of doesn't matter, because if you think about the timeline from the standpoint of main, when you create the thread and then call and launch the do work function, there is no pause in the main thread. It moves right on to the next thing. So it's not waiting on anything that's happening in the thread. It's waiting on the join, right? It's actually gated on the join. So as long as it's before the join, that's really the point you're going to be waiting on. All right, let's look at that. And get rid of that. Catch up to where the slides are. I really have to find that feature that lets me skip slides instead of individual animations. But so here we go. There's our main. We got our thread instance. We're launching it with do work. We could also do it this other way. We could say my thread to declare the instance and then set it equal with the assignment operator, right? Actually, that might be a copy operator between instances, right? So we invoke the thread library again and pass in do work, and that just gets passed over. That's a typo there. I should have put in a comma 10. I updated this to add an argument to it. Forgot to add that. But then there we go. We rejoin and we're set. So hopefully you saw kind of this thing gradually printing out a message, working on item 1, working on item 2, et cetera, when you ran that. And if you didn't slow that thing down, you might not have an appreciation for the order in which these things are occurring. But you should see the waiting for work to be done happen kind of before the first printout from do work. But there's really no guarantee that the do work might not print out its first thing before you're waiting for work to be done gets executed. There's really no rules about who's going to win that race, right? So the minute you fork that thread do work, they're both racing to do the next thing as fast as they can. And there may be some prioritization that the main thread might have, but as we're going to see in some of our exercises, these things could collide with each other, and one could write right over the top of the other one and make a mess out of your console where you have trouble reading things, right? So let's see if I missed any key points here, right? Yeah, just a reminder not to do the parenthesis and the join, and yeah. So those are kind of the key points. So let's do a slightly different example. Any questions on that, by the way, before we move on? Okay, and I'll try to keep an eye on my chat window too. All right, so let's look at a different example. So in this case, and this is kind of analogous to the havoc situation in many mathematical functions. So we may have a bunch of jobs. We don't really know how long each one of them are going to take. Some may finish immediately, some may take longer. And so we kind of need all of them to finish before we can aggregate some data, let's say, and move on to the next part of the process. So we can use the main thread kind of as a conductor that's going to block. People often talk about thread blocking or thread locking. So our main thread can block intentionally while it's waiting for these other things to finish. So let's say if it was a car, we build some tires, we build the engine, doesn't take very long. We build the chassis, that takes slightly longer. And then we want to assemble the car, right? Based on, some stuff that's been produced by these other threads. So how would we do that, right? So first off, this time we'll have different, well, just for the sake of making them different, we'll create different worker functions. How many tires are we going to build? And then it'll follow the same model that we saw for our worker function before. We'll pass an integer that is kind of the amount of work. And the printout is going to indicate which tire we're building, the 0th tire, the first tire, et cetera. And then we'll sleep a little bit. And what we want you to do is actually come up with, see if you can figure out how you would actually do that using what you've learned so far with the join, right? So we're going to need to have these 4 worker functions that are already written for you. You're going to want to create 3 separate threads, one for working on the tires and the engine and the chassis first. right? You can decide how many items you want each of those threads to work. And then you want to have those rejoin the main thread, right? And then for the sake of just doing it outside of the main thread, call an assembly thread after that, and then have it kind of assemble the cars. It's all contrived here, and then rejoin your last thread. And then print a message to indicate when you're done. So give that a try. Hopefully I got the links right on this one. Let me know if anything's missed there, and I'll post those links again. And also, if anybody does not see the link file, let me know. I'm happy to repost it again. But give that a try, and I'll go back to the previous slide in a minute. Let me just actually set my timer so I don't forget. And I will peek at the code and just make sure there are no gotchas here. And if you forget any one of those 3 threads, you'll experience, and it may be worth, if you get this done early, commenting one of the joins out. Don't rejoin a thread and see what happens. Might be worth trying that out. Okay, another half a minute or so. All right, let's take a look just to make sure everybody's together on this one. So I won't go through all the functions because those are written for you, but here we're just kind of launching our threads, right in the constructor arguments, passing. Again, the 8 is an argument for build tires. And if each of these functions had different numbers of arguments, you would, of course, have to list out different number of arguments there. It's all going into the constructor for thread object 3, which is from the thread class, right? So hopefully all that makes sense. And then we rejoin each of those. And I probably left out my message printout here, but and then we'll go ahead and launch a thread to go off and do the final assembly. Maybe we're aggregating information here or passing in things that maybe got worked on by these individual threads. We're coming up to that point where we'll talk about how we pass data back and forth between these threads. But that could be where we would aggregate that stuff and do something. And then, of course, we have to rejoin that thread before we can exit, right? So we're out, right? So that's a pretty clean execution. You can structure those to however your problem actually works. And, there is diminishing marginal returns here if you, create, 500 of these threads. Let's say you got a whole lot of tires. Maybe you got 1,000 tires to build, but only 2 engines. You could actually launch 2 different threads working on the tires at the same time and divide up the tire problem between multiple threads, right? If you've got a fast enough computer, then that's okay too, right? And it's all about designing your problem space, chopping it up so you can kind of attack it in this way, okay? Right. So now, any questions on that actually before we move on to dealing with data?
Just give me a second. I'm going to look at this. Oh yeah, you have to join the thread at the end. I forgot to join my last thread.
Yes, exactly. Yeah. What did it say? I forgot what the error looks like.
Terminate called without an active exception.
Okay. Yeah. Yeah. You'll notice. I mean, as most of you probably learned by now, as I've said, if you If you have warnings, or if you have a segmentation violation when your program exits, it's generally not a good sign. So that's probably what's going on there. And we'll see a bit of that for sure. That stuff happens with threads. Okay, so let's move on to the next interesting challenge here. So managing inventory. And by this, I mean, how do these threads collaborate with some kind of memory that we would like them constructively to utilize, right? So maybe we have some common integer, just a simple integer. It could be a whole class, an instance of a class, but for the moment, let's say it's an integer called grommets, and it's some inventory that we want to sell, right? And that we want to have multiple salespeople trying to sell the supply of grommets as fast as they can, right? But obviously, we don't want to sell grommets we don't have. So we have to be really careful to make sure that, before anybody sells a grommet, they have to make sure that there are grommets available. And so they're going to need to be checking this variable. But how do they do that from inside of the worker function? And what happens if each of these threads decrements the grommet at the same time the other one's decrementing the grommet, right? What happens? Who wins? And how do we actually control that? That's the problem that we're trying to solve here. And we'll explore it in phases like we did on Tuesday. We'll kind of look first at a couple bad examples and see exactly how and why it fails, which is instructional. But let's first redesign our worker function here a little bit. So we're going to treat our worker function as just a salesperson. We'll give them a name so we can tell when we print out our debug output who's doing what, because it gets pretty confusing pretty fast. We're going to give them a pointer to the inventory item, number of grommets, number of shirts, whatever that is. And notice we have a star there, which means it's a pointer to an integer, right? So the idea is this sales function, this salesperson or this function is going to check that value and decrement it whenever they sell something. And they may have a delay before they can go ahead and sell the next thing. It's like a recovery time, right? So you would do the logical thing. You'd say, oh, well, while the dereference, while what's at that inventory address is greater than 0, I should be able to sell, right? So I will say so-and-so just sold item number, and we'll use the count of the inventory as the thing that they just sold, right? So we just sold that thing, and then we're going to decrement what's at that address, right? So we dereference, and I put parentheses around it so I can use that decrement symbol. You don't want to, just whenever you're in doubt, feel free to use extra parentheses. And then I will sleep, right? And so sleep here is just going to represent a recovery time before I can turn around and sell the next one. And keep in mind that every other salesperson is going to be doing the same thing, right? And this is not our ideal solution for sure. This is just kind of would seem like a logical way to go about doing it, right? And again, that the inventory, just to be clear, when I say sold item number, it doesn't mean I sold 10 things. It means I sold the 10th item 10 and item 9, item 8, etc. Which I realize that's a little confusing after I first wrote that. Okay, so let's look at main. So we have our inventory set up. I'm going to create salesperson A, and I'm going to call the worker function. I'm going to pass in the name of salesperson A. You can abbreviate that any way you want. Pass in the address of my inventory item, which is grommets in this case. And I'm going to start out delaying 0 seconds. So these salespeople are going to be super fast. They are not going to pause between any attempt to sell these things. As soon as they sell one, they're going to whip right around and try to sell the next one. Okay. So we'll set up a bunch of salespeople and we're going to let them run, right? And so let's take a look at what happens, right? If I have something like this, where I say, while what's at inventory is greater than 0, that might very well be true. And in fact, it probably is true in that moment. But in the moment between when I execute that test and when I actually decrement it, some other thread is actually assessing its value as well. And it says, oh, it is greater than 0. I can sell one too. So it decrements, and then the other decrements, and now we have negative inventory, right? Because they both just happened, not always, but it just happened that they were testing that while condition right about the same time. And the really, really terrible thing about debugging threading code is because these things don't fail in the same way every time. In fact, they may not fail for a really, really long time until, for example, two threads happen to test in the same fraction of a moment, right? So you can't create the conditions under which these things are necessarily going to fail. You have to implement good coding practices to avoid that, right? So that's the real problem. That time gap between what happens when you test and when you do the decrement opens up a window of possible failures for all the other threads trying to do the exact same thing, okay? So let's look at that. So you guys can just kind of run this. There's nothing for you to have to do, but let's start with it at 0 delay for each of the salespeople, right? I think it's probably set up at 0 delay, and see what happens. Run it about 5 times and see if you get negative inventory. It's interesting because you don't get negative inventory right away, but look at who's selling. Look at whether all the salespeople are selling the same amount of inventory or not. Is one salesperson selling more, or all, or most? And you'll see that it's not deterministic. Every time you kick this thing off, after you do 3 or 4 or 5 of these things, you'll start seeing some variance in the results that come out. So try that for just a minute or so, and then we'll talk about maybe what's going on there. And you'll probably see some mangled output in your console window as well, which we'll explain in just a second. I'm going to run mine here too, just to see what I get. And again, watch who sells the most. It's very interesting how different it is every time. And then we'll talk a little bit about why. Does anybody get negative inventory? Hopefully you're seeing that.
Yeah, I'm getting a bunch of negative inventory, and I'm even
Okay.
getting, statements being interrupted in the middle.
Yes, yeah, exactly. Yeah, it's quite fascinating. Well, let's talk about that a little bit then. Just clear my screen a little bit of some stuff. So, right, so here's one example of my output, just to be illustrative about this. So notice sort of salesperson A, wins the first 2 sales, right? So in the time that we send off thread A for salesperson A to start working, they execute two loops, basically 2 sales before we even get to the next thread, right? But the next thread isn't B, it's actually E, right? So B, for some reason, we don't know, it's not deterministic, B doesn't get spawned right away, right? It doesn't actually get spawned until the very end down here. So E jumps in and it gets 3 sales off. And before this output can finish, this yellow output, A has sold something else. And because our console is just receiving output from all of these threads at the same time, we have, unfortunately, no easy way to sort of divide this debug data. It would be nice if you could divide it into columns, right, by thread or something like that. And I'm sure there are debug tools that let you do that, but not here on Replit. But it makes sense, right? They're all executing at the same time. There's no guarantee that any output to the console is going to be allowed to finish before it gets interrupted by this other thread. And then, of course, as you can see, it can end up with negative inventory. So that's the problem, and it really revolves around just this one integer, right? This one integer that we were given. We need to find a way to lock it off so that it can't be accessed while someone else is using it, okay? And that the reason for getting into what we call mutex, right? So I think we talked about most of this stuff. Let me just double check. It's here for you to come back to. Right. So the key thing, this bullet right here, the key thing is, in order to solve this problem, we need to stop these threads. So threads that are wanting access to a particular piece of memory, if it's critical that they get it at a particular juncture, we have no choice but to just stop that thread. We need to put that thread to sleep until that piece of data is available and some other thread has released it. So we need a way to lock a piece of data, or at least, if you ever played capture the flag or something like that, the flag is not the thing, the data is the thing, but we can raise a flag and say, hey, this is off limits right now. I'll drop the flag when it's okay. So that's what these locks are all about. They're like flags that just indicate when it's safe for a thread to go work on some data, right? So, and the key is to stop those other threads. So here's how we might think about doing it. You might think, okay, I'll just create another variable called isLocked, and I will just set that variable to true or false, right? So one thread will grab it and say if it's not locked, then I will go ahead and lock it, and then I'll do some stuff, and then I'll unlock it, right? You might think that you can do that by just creating a variable to lock that. But the problem is that that test suffers the same challenges as the inventory test above it in the while loop. In a moment where we say, is it not locked? And we think, oh, it's free and clear. Somebody can come in and grab it away from us. And so we end up thrashing this same piece of data the way we would have been thrashing the inventory up here. So that approach really does not work for us, right? It's not the way to go. We need something more specialized than that, right? So, and that's where the mutex class comes in. And this is pretty easy to use, but conceptually, without getting too much into the guts of it, the idea is we just want to raise a flag that says, hey, this particular mutex here is busy, right? And anybody who checks that mutex and finds out that it's locked will actually go to sleep, right? So the act of actually checking the mutex, you'll either get it or you won't get it. And if you don't get it, you go to sleep. That's the key thing, right? You just pause and wait. And so we can define these things in any scope, and it can be global or it can be passed around from function to function. It's just an instance of a class like so many other things that we have been using. And any thread, by agreement, that wants to get access to a piece of data has to check the corresponding mutex before it goes and tries to do something with that data. Right? So if I get it, I can continue, right? And if I don't, I am blocked, right? That's what we say, the thread gets blocked. It just goes to sleep. And there can be many, many threads all blocked while the happy thread up there is modifying the data. And when that data becomes, when that mutex gets unlocked, there's no line or queue on who gets to have the mutex, right? As soon as that mutex is unlocked, it's a free-for-all. Whoever can get it next, including the thread that just had it, has an equal chance of getting that mutex back again. It's not deterministic. So, and there are systems that can implement sort of a thread queue, but at this particular level, it's just a free-for-all. So when it opens back up again, anything, the first thing to grab it gets it, right? But the key, at least we have this flag that we can use on inventory or something like that to prevent us from having these problems. And that's really key. So let's try to look at how that would go. So we create a mutex, and inside of main, and this is going to be global, unlocked, right? We're going to call it our inventory mutex. And now we have our inventory variable, right? These are not connected in any way. This is just a flag that we're going to raise or check from time to time by agreement. So now we'll say thread salesperson A, pass in the inventory address, and we'll see that our worker function actually has access to this global variable, right? So they're all going to just agree to, inside of our worker function, consult this mutex. So whoever gets the lock first can continue. So a thread that's executing this worker function with that loop, if they're the first ones to get to this point, they secure the mutex, and they can continue. Otherwise, they go to sleep and they wait. But if you do get to continue, the next thing you want to do, and then you know it's safe to do, is to check the inventory, because you know you didn't go to sleep, right? If you went to sleep, you just won't proceed, right? You'll just wait. But if you did get the lock, you'll proceed, you'll check the inventory, you'll sell the item, maybe decrement the inventory, sleep for a minute or two, and then the most crucial thing is you have to remember to unlock the mutex, okay? If there's no inventory, you still have to unlock the mutex and return from the function, right? But at a minimum here, what we've done is we've protected this particular salesperson's right to sell inventory if it's available. Now, think about what happens here. Let me make sure I don't. So we're going to loop again, right? As soon as we, in this particular implementation, as soon as we unlock, right, we're going to loop back around in either one of this if or else. We're going to loop back around and try again to reacquire the lock. But in the time that we wrap around, try to reacquire the lock, someone else may have already acquired it, right? It might be us, like we might actually get lucky and reacquire it again, but it might be another salesperson. And if another salesperson grabs it, then I'm going to sleep and I'm just going to sit here until it opens up again. And the minute it opens up, I'm competing with 8 other salespeople to try to grab that lock. And there's no guarantee that I'll be the one to get it, right? So but that's what our mutex does for us. It allows us to have this agreed upon flag that prevents us kind of from running through negative inventory there, or whatever the case may be, okay? So here's a visualization look at that. So we go do some work, and this is a little bit heavy. I apologize for that, but I wanted to give you a picture of it. So here are our 2 threads, and main is going to wait here for the rejoin, right, for thread 1. It's going to wait here for the rejoin of thread 2 and thread 1, right, to finish. And there's our mutex. So let's say that thread 1 gets it. So it secures it. It's going to lock it, right? And it's going to start doing work right away. Meanwhile, moments later, thread 2 comes in and says, hey, I want the mutex. Well, thread 2 is going to go to sleep, right? Because the mutex is locked. So thread 2's got to wait. It's going to be waiting there until we do the unlock, right? Over here in thread 1. Now it's back open again. And both of these are going to try again at the same time, right? The do work function, according to that code that we just saw, is going to loop back around and try again to reacquire the mutex. So it's competing immediately with thread 2. And there's no guarantee that either one of these is going to have an advantage over the other one. So, but let's say we run out of inventory eventually through that whole process. 1 rejoins, and then 2 rejoins, and now we can finish, and the whole program finishes. Okay, so that's how we would use a mutex. Okay. So let's look at the code for that. This is just setting you up for our next exercise, but let me pause, take a breath there, and see if anybody has any questions on that before we kind of move to our new exercise. It's kind of a big picture to look at. Any questions? Everybody got that okay?
Both new thread 1 and 2 do work, unlock, and try again, right? If they can.
Say again, sorry?
Well, the arrows after the mutex.
Oh yeah, so the orange one is just sort of trying to amplify that idea that thread 1 is in the running for the next grab on that lock because it's in a while loop, right? So this is kind of that while loop. It's implying it's going to keep looping as long as it has inventory. Yeah. And so you might think that it has an advantage over the other ones that are waiting, or you might think that the other ones that are already waiting have an advantage over this one because it has to loop back again. But as it turns out, there's really it's not deterministic. It's apparently random at which one gets it.
Yeah, and so those arrows after the circle, he could apply to either one.
Oh yes, true. Sorry, yes, exactly. That's absolutely true. Sorry, yeah, yep. Trying to fit it all on one page there. Okay, so let's look at what we're going to do then for our next exercise. We're going to try to formalize our inventory as an instance of a class. So it's going to be relatively simple, but it's going to pull in some concepts that hopefully you guys remember. First off, here's our inventory. We're going to call it quantity available, right? So when we instance the inventory, it's going to have a certain quantity available. And because of this printing problem of finding out which salesperson has done what, we're going to kind of take advantage of our knowledge of the map so that we can store an increment for every salesperson. Whenever a particular salesperson by name makes a sale, we'll increment how much they've sold, and we'll keep it in this key value pair, this map here, right? And that way, after all the inventory is gone, we can just consult our sales history here and see who sold what. We don't have to worry about stomping on each other in the output file, right? So here's our constructor. So when we create the inventory, we basically just say, hey, I want 10 grommets or whatever, and it's going to initialize the quantity available to that, okay? And it'll print us out a message, let us know how much inventory we have. And that's all we got to do, right? That's just our simple inventory instance. And then we have our global mutex like we saw before, okay? So what we're going to do is going to have you take advantage of this class and incorporate the lock and the unlock in the framework code that you've been given. And I'll tell you, there's really kind of 2 or 3 different ways you could do this that are not particularly wrong, right? You can decide how you want to construct the policy so that, like, maybe you want the first person to get the lock, be able to sell until all the inventory is gone. Maybe you want to force them to relinquish the lock so someone else can sell some inventory. So you can kind of play around with that a little bit and see what the behavior is like. And hopefully the printouts and the sleep will help you there. But basically, go ahead and in main, create these salespeople, give them a name, and then you can decide how long each one has to sleep before moving on to the next sale. So there's a lot of numbers you can play around with. I'd say just kind of get it up and running first. Make sure you're not crashing. Make sure you're rejoining the threads, and then just play around with a couple of those settings and see what kind of insights you can take away from that. Okay, and consider that the most important thing is you have to release the mutex in either of the if-else blocks, right? If you leave the function without releasing the mutex, you'll definitely hang the program. Okay. So give that a try. I'll give it a couple minutes, and then we'll talk a little bit about some insights. Now, you may find the syntax a little confusing with the map. I did, if you recall, we usually want to check the count. So sales is the sales history. So we say if sales history for a particular salesperson count is 0, then we know they haven't sold anything yet. So that might help ring a bell for you. And we'll have one more quick one after this. So if you guys can bear with me, I think we'll be able to get you out of here in about 10 minutes tops. So the 2 key things to remember really are unlocking your mutex and rejoining your threads. Those are usually the things that will trip you up in the end. And sometimes it's a little confusing when you create your threads. You have to kind of look at your worker function and see what arguments they're actually looking for. Remember not to use the parentheses on your worker function when you feed it to the thread. That's the important thing. Okay, we'll just give you a couple more seconds on that one. Make sure everybody has a lot of time on that.
Cool. Sometimes one thread will do all the work.
Yeah, right, exactly. Yeah, so figuring out kind of, how to balance your threads is sometimes quite the name of the game, right? It's interesting to see how all that stuff pans out. So yeah, so here's that slide. So this is just main. I think did I go actually? Did I? Guess I didn't talk about exactly. I mean, essentially, there's no wrong answers as long as you unlock your thread. You can come up with different strategies for either releasing the thread after one sale, or you can have, make it be greedy, let the first person to get to it sell all the inventory. Probably not very realistic in that way, but it really depends on the kind of problem that you're modeling. Yeah. But you can see how, I mean, it's really tempting to think about concurrent processes that happen in the world like threads. So, things you kind of, from a programming standpoint, you're like, I don't know quite when it's going to finish. It's going to spawn some threads. I really don't know where it's going to go. It's not specifically deterministic, but I can model it with threads, right? I can have all of these different processes and just sort of watch the system evolve, which is pretty fascinating. I mean, there is a practical limit to the number of threads. You couldn't have the population of the United States where every human's a thread. That wouldn't work. But you could do population centers or something like that if you're modeling something like people or behaviors. It's kind of cool. So there's our kind of insights, just things to be aware of. And not waking up is always just about the worst thing, because then you got to figure out who didn't wake up, why didn't it finish, why is my program hanging, and you kind of got to go back at your worker threads and look your code. Or if you have a first-rate debugger, you can probably find that stuff out more easily than in Replit. Okay. So let's talk about one more thing, and thank you for sticking with us here. We're going a little longer than I thought, but it's worthwhile, I think. So so imagine, let's see if I can make this clear. So this is our kind of model we've been talking about. We have these two threads, we secure the lock, we lock it, we do some work. Somebody else is waiting on the thread. So they are waiting on the lock, sleeping. And there's a little loophole in the code for your worker function where you forgot to unlock it. Maybe the inventory was 0 and you didn't sell anything, so you thought, why do I have to unlock? But you just returned to the main thread. Well, we're going to get stuck here at this point in main, waiting forever. Or even if we swap those two joins places, we're still going to get stuck and your program's never going to finish. So, I mean, this is a classic thing, return code logic can get pretty confusing, and, it's understandable that this could happen, but it's a really nasty problem. So what can we do to try to help stop this thing from happening? Well, if you recall, if I can find my cursor here, where'd it go? There we go, I think. Sometimes it just goes away. I think Zoom is eating all of my resources. There we go. Sorry, it was actually locked up. So so the lock guard is a solution to that particular problem. It's not the only solution, but in the same way that we use shared pointers to clean up memory that was on the heap when something went out of scope, the lock guard is an almost identical concept for unlocking a mutex when the lock guard goes out of scope. So rather than creating just the mutex, we can actually create a lock guard in the local scope of a worker function. And then guaranteed when either that scope or that function returns, because of this auto cleanup process that we saw implemented in our shared pointers, lock guard does the same thing. It says, hey, I'm going out of scope, I'm going to call my destructor, and my destructor is going to always unlock the mutex that I was initialized with. And so this is that RAII concept again, we're seeing where it's like, hey, clean up after yourself. Well, in this case, as long as the lock guard is given the mutex when we start out, it's going to clean up the mutex, and we avoid a significant number of deadlocks that occur from maybe just bad coding or cases we didn't anticipate, right? So this is that idea, and there's how we do it. So the name of the class is called lock guard. The template type is mutex. We're guarding a mutex, right? And it's just a scope bound guard. And so I call the instance scope lock, but you could call it anything you want. And what we pass it is the actual mutex instance. So we create the mutex instance above, and then we lock it with the lock guard. And what we're going to pass around is the scoped lock, not the inventory mutex. Because the scoped lock, when it goes out of scope, and it could be called anything, but once that variable goes out of scope, it's going to unlock that mutex. That's the next level up on this thing. So here's kind of how that might work. So I have a lock guard inside of the scope, and the inventory mutex already existed, right? And so we've acquired the lock by virtue of actually creating the scope lock. We are either sleeping or we're acquiring the lock, right? So this is the equivalent of acquiring the mutex, but we've actually wrapped it inside of this instance called scope lock. So if we acquire it, we can move on. If we don't, we go to sleep there. But let's just say we actually acquire it, right? So now we continue, we do all of our particular work that we need to do. And as soon as that scope is passed, we've returned from the function or left some inner scope, it calls its destructor, releases the mutex, and now all the other threads can have at it. So it's a little bit cleaner. There's nothing specifically wrong with what you guys just did with only the mutex, but this is kind of an increasingly modern way to deal with these kinds of things, is seeing them wrapped in a way that, when the scope is over, they clean up after themselves. So that's just a really the modern way of doing that, okay? So I think this tries to just graphically illustrate that. Let's see if it's actually intelligible. So there's our lock guard that we acquire or go to sleep, right? So this guy right here is going to try to acquire that scope lock on the mutex, but go to sleep because it's busy, right? Go do work. We return from our function, or the lock guard goes out of scope, and then thread 2 can acquire and finish, okay? Same thing we saw before, just we've wrapped it inside of something that just helps us avoid some typical problems, okay? So, and then I think, let's see, there's a key point here. Right, yes, this is a nasty bug, okay? And I'll just remind you here, and when we get to our threaded homework exercise, undoubtedly folks are going to do this, and I'll try to remind you as much as possible. If we acquire the lock guard more than once in the same thread, which can happen, you compound the locks. You create multiple scoped locks, all waiting on the mutex. So it's really important that you don't try to reacquire the same lock inside of the same thread that already has it, because you will put yourself to sleep basically and not exit the program. So you want to just be conscious of the fact that if you did it inside of this loop here, you acquire the lock and you loop back around and you try to acquire it again, well, you're still holding it because this thing hasn't gone out of scope, right? So this is just a gotcha situation that you just might want to make a small mental note to come back to if you find you're really lost in why your program won't terminate normally, okay? So I think in the interest of time, considering how late it is, I'm going to leave this one for you to do on your own time. And I do encourage you to look at it, because we're going to have a little questions on that. And then next time we'll look at conditionals and detaching threads. But I also wanted to offer to you a suggestion, if you have the time, to try to take on this little Lab 26 challenge. So a simple guessing game. It doesn't have to be as elaborate as your homework one. But the idea here is you have separate guesser threads that are trying to guess a secret number that the main thread is holding. So taking what you know, the idea would be try to come up with a simple design with the stuff that we talked about today so you could implement this multi-threaded game and see if you can convince yourself that only one guesser thread is actually winning, right? The error would be if both guesser threads think they guessed it correctly and declare themselves the winner. That would let you know you haven't sufficiently locked off the guess. So you only want one thread to be able to guess at any one time, okay? So that's just a suggestion, and we'll go over a solution for that on Tuesday just so you can see how I did it. And other than that, that's it. And I hope you guys found this interesting. This is one of those other definitely ninja topics that is worth knowing in any language, really. So hopefully it's a little inspiring. If you have questions, I'll be here. Otherwise, I'll see everybody on Tuesday. And have a great weekend.
All right.
Thank
Thanks,
you.
Professor. Cool stuff. See you later.
You're welcome. Bye.
I was just curious, is
Yes.
it possible to acquire like how many threads a computer has from the system in C++ and similar stuff like that?
That's a good question. You mean how
Like
many
actual
are
or threads
from?
instead of virtual threads?
I don't know. I think considering the way it's probably it's operating system dependent. There, I forget. There's a way in some languages, I think C++ can do this, but where you can say, only give me a physical thread. I don't want a logical thread.
Yeah.
And by virtue of that, you can, control it. But I think it's probably considered to be quite the no-no to try to lock to physical threads, unless you're on a really dedicated special system like Arduino, not Arduino, but like an embedded system.
Yeah.
Yeah.
So I was just curious if it was or like you're trying to use as many threads as you can in larger projects, but how would you know how powerful the system is?
Yeah. No, it's true. Yeah, I think from a load balancing standpoint, that's a good question because I think because if it's a multi tenant system, you may not be able to really know what other demands are being placed on it. Now, if it's just
Yeah.
program, then that's something else altogether, I guess. I mean, it's really interesting in the context of servers, cloud-based servers, because they're definitely doing this a lot, right? It's like, I'm going to time slice, this device or this program maybe on a multi-tenant system and then put everybody else to sleep for a few microseconds,
Yeah.
So I would not want to be an operating system. It's not my bag.
Yeah. All right. Thank you.
You're welcome. All right. Have a good night.
You too.
Bye.